The speaker. So our next talk is by C Dreyer, also from Rutgers, and Cyrus will tell us about current density implementation for calculating flexoelectric coefficients.
Thanks for the introduction. This work was done in collaboration with David Vanderbilt and also Max Stengel from Barcelona. So we just heard a lot about piezoelectricity. I'll just remind you what flexoelectricity is. So flexoelectricity is polarization that's induced by a strain gradient as opposed to a uniform strain. And you could apply a strain gradient to a material by, for example, bending it or some non-uniform compression. So we're interested in flexoelectricity for a couple of reasons. One of them is the possibility for novel device designs, for example, piezoelectric type transducers with non-piezoelectric materials. Also, large strain gradients can be present in nanostructures unintentionally, for example, at heterostructure interfaces, and therefore the flexoelectric effect could play a large role in the properties of such devices. So from an atomic point of view, the flexoelectric effect is pretty intuitive. We apply a strain gradient, for example, by varying the x strain with x position. Then we create a non-symmetric environment, in this case in the x direction, and therefore we will induce dipole moments in the charge density and non-zero polarization. So the way that we discuss the flexoelectric effect, just like the piezoelectric effect, is through these flexoelectric coefficients that relate the polarization, for example, in this case in the x direction, to linear order to the strain gradient. So in our example of a longitudinal type strain gradient, also in the x direction, all of the four indices of the flexoelectric coefficient are the same. Of course, we could have a variety of different types of strain gradients, including shear and transverse, and then also longitudinal. And so a general flexoelectric coefficient will look kind of like this. So our goal is to calculate all of the flexoelectric coefficients for a given material from first principles density functional theory calculations. And so if you've been coming to this meeting for a while, you've probably seen presentations of some previous work calculating flexoelectric coefficients, both from David's group and also Max Stengel. So I won't go into any of the details of these two implementations. They have a lot of interesting differences, but one thing that they share is the fact that they require calculations of large supercells in order to access all of the flexoelectric coefficients. And this is computationally intensive, especially if we want to calculate these coefficients for a variety of materials with a variety of symmetries. So we would like to calculate the flexoelectric coefficient from a single unit cell calculation, just like the density functional perturbation theory implementation to calculate piezoelectric coefficients that we heard about in the last talk. So in this talk, I'll just go over briefly our approach for calculating the flexoelectric coefficients from first principles using density functional perturbation theory on a single unit cell. And then at the end, I'll give some examples of our calculations for cubic oxides. So the first question that we have to answer is, how do we model a strain gradient in a bulk material? It's not even obvious, since we've broken the translational symmetry of our crystal with a strain gradient, how to define a unit cell. So the approach to doing this is to realize that we can identify the different types of strain gradients in different types of acoustic phonons. And so if we treat a strain gradient as a very long wavelength acoustic phonon, then we'll recover the periodicity that's necessary to do a bulk calculation. Of course, we don't want to try to create a supercell that will capture this long wavelength periodicity, but thankfully we don't have to, using some well-developed methodologies in density functional perturbation theory. We know that we can describe the atomic displacements of sublattice kappa as a result of a phonon with a cell periodic part modulated by a phase with wave vector q. And in the linear regime, we can also describe responses to these atomic displacements, such as the polarization response, also as a cell periodic response modulated by a wave vector, the same wave vector q. And so if we're smart about factoring out these phases, we can just focus on the cell periodic parts of these, this displacement and response, and therefore only do calculations on a single unit cell. So in these schematics, these dots could correspond to a single atom in a unit cell, or they could correspond to a unit cell themselves, which in a general crystal may have several atoms. So this was touched upon in the previous talk, that in that case, you have two contributions. You have a frozen ion contribution, or in the previous talk, a clamped ion contribution, which is, again, the purely electronic response to the strain gradient. And then you also have a lattice-mediated contribution from the internal relaxations caused by the local strain and strain gradients. So in this talk, I'll be focusing on the frozen or clamped ion contribution. If you're interested in discussion about the lattice-mediated part, then I'll refer you to these references. So just briefly, the way that we calculate the frozen ion flexoelectric coefficient is by calculating this cell periodic polarization response that I mentioned before, and taking its second derivative with respect to phonon wave vector. So this would be a calculation for a given phonon with wave vector q, and then we take the second derivative in the long wavelength, or q equals 0 limit. So that's how we describe a strain gradient. The second question is, how do we calculate this polarization response that I've been referring to? So kind of in the schematics that I showed before, they were based on looking at the induced charge density from a strain gradient perturbation, or a phonon perturbation. And the induced charge density from a phonon perturbation is something that's readily available in most DFT packages. And it's been used in previous implementations to calculate flexoelectric coefficients. Unfortunately, we see that since the charge density is given by the divergence of the polarization, it only contains information about the longitudinal components of the polarization field. And therefore, from the charge density in bulk, we can only calculate the longitudinal flexoelectric coefficients. If we want to calculate the full flexoelectric tensor from a bulk calculation, then we need to instead consider the current density that's induced by a time-dependent motion of atoms, which we know from electrodynamics is related to the polarization in the following way. So this current density is not something that is normally implemented in density functional theory, and so we have to develop our own methodology for these calculations. So in the next few slides, I'll just briefly touch on a few aspects of this methodology. So if we want to calculate the current density, we can start from the basic definition of current density in quantum mechanics. So we know that current density is defined by the continuity condition, which just specifies that if the charge density changes, then a current has to flow. If we combine this with the time-dependent Schrodinger equation, we get this familiar form of the microscopic quantum mechanical current density, which depends on these derivatives, spatial derivatives of the wave functions. So this is all kind of textbook material. However, it turns out that in the context of density functional theory, this current density is problematic for our purposes. And the reason is because of the ways that we describe the core electrons in a density functional theory calculation. So to make our calculations computationally tractable, what we do is we, in a cutoff radius, RC, around the atomic nuclei, we treat the wave functions and potential as kind of smoothed versions of the full all-electron wave functions and potentials, so-called pseudopotentials. And for some technical reasons that I won't get into right now, almost all modern pseudopotential implementations involve non-local operators in the potential operator. So if you apply to a wave function, you have a local operator and then a non-local operator that is in the form of this projector, in this case over angular momentum channels. And so these non-local operators cause a lot of problems for a physical interpretation of current density. The reason is if you apply a non-local operator to a wave function, you can have these unphysical and discontinuous motions of charges where charge can kind of teleport to different places within the cutoff radius. And so this kind of charge teleportation is allowed in Star Trek, but it's not allowed in physics. And so what we have to do is make sure that when we define a current density, that it still satisfies the continuity equation even with the possibility of these teleportations. So it turns out that this definition of the current density actually does not satisfy the continuity equation when these non-local potentials are present. And so we need an alternative definition of current density in this case. So the way that we obtain this alternative definition is, again, from classical electrodynamics. We know that we can write the energy stored in a magnetic field in the following way, and we can relate this to a product between a vector potential and the current density. So here we have a relation between the current density and the energy, and so we can use that to develop a quantum mechanical operator, a current density operator, that is the derivative of the Hamiltonian in the presence of a vector potential, which will describe our phonon perturbation, the derivative with respect to the vector potential. And so I won't go into any details of how we actually calculate this. You could ask me after the talk. But this definition of the current density actually satisfies the continuity equation and gives a physically meaningful value for the current. So the induced polarization is something like a matrix element with this current density operator. We still have the fact that our atomic motion is time dependent, and therefore these wave functions are time dependent. And the fully time dependent wave function is also not something that's readily available in density functional theory. So the second question would be, how do we treat this time dependence? And the way that we do that is if we, again, start from a pristine crystal, and then we slowly move the atoms to create this strain gradient, then we can write the fully time-dependent wave function parameterized by this time-dependent atomic motion lambda as an expansion, the sum of the static wave functions at a given lambda plus the first order adiabatic wave functions, so first order in the velocity of the atoms. And again, I won't go into too much detail, but it turns out that these first order adiabatic wave functions can be calculated using quantities that are used, for example, in a static phonon calculation, specifically the first order Hamiltonian. So using this adiabatic expansion and our alternative definition of the current operator, then we can calculate the induced polarization that we need for the flexoelectric coefficients. So just in the last few minutes, I'll just give some simple examples of these calculations. So I'll calculate frozen ion coefficients for very simple material cubic strontium titanate. For this symmetry, we have three non-zero flexoelectric coefficients, a longitudinal, shear, and transverse coefficient. And again, I'll remind you that we calculate these flexoelectric coefficients by taking the second derivative of the polarization with respect to Q. So this is an example of a calculation. We have induced polarization versus Q. We can take the second derivative of these curves, this polarization in the x and the y direction, and therefore obtain the clamped ion flexoelectric coefficients. So compared with previous calculations, which are highlighted in blue, we have very good agreement. But of course, I'll remind you that these new calculations were calculated on a single unit cell and didn't require the computationally intensive supercells of the previous calculations. And because of this, we can perform calculations on a large number of materials. Here I just show other perovskite oxides all in the cubic phase, and then a slightly different material, magnesium oxide. And we can calculate, again, not just the longitudinal, but also transverse and shear coefficients very efficiently. So just to conclude, I've given you a brief overview of our approach for calculating the frozen ion flexoelectric coefficients by modeling a strain gradient as long wavelength acoustic phonon and calculating the current density response, and then given some examples of cubic oxides. Thank you.
Okay. Rafael?
In the simplest case of piezoelectricity, one distinguishes carefully between polarization in zero field, polarization in depolarization field, open circuit, short circuits, like. Now here in flexoelectricity, everything is very complicated. You cannot think in terms of zero field or whatever. For instance, if you compute mu x, you always have the polarization field. Now, I remember of a very elegant paper by Max Stengel on change of the metric and the like, but I don't see well how this comes into these Q derivatives. So where is the field hidden in those Q derivatives?
Yeah, great question. So I didn't go into this, but there will be, in principle, if you're not careful, there'll be discontinuities of the polarization at Q equals 0 due exactly to this electrostatic boundary condition problem. So in our calculations, what we do is we, in the calculations I've shown, we enforce short circuit boundary conditions by, in reciprocal space, these reciprocal space derivatives, removing the G equals 0 term in the electrostatic potential. Yeah, so exactly. So kind of maybe a physical picture of how we remove this by removing the G equals 0 term in the first order potential is similar to having, in the case of piezoelectricity, the argument of having a kind of a diffuse, free charge that screens the long-range electric fields. So it is taken into account, and as you said, the metric implementation which we're working on so it also kind of treats this.
So have you found any surprising materials with large coefficients?
Yeah, so that's kind of the next step. I think now that we have a methodology that we've seen in kind of the materials that we've studied before works well and is efficient, especially for materials of different types of symmetries. That's kind of the next step, to combine it with the lattice-mediated part and to start searching for interesting materials.
Thank the speaker. So last talk of the session is by Kyohei Takaya.